Yeah, so it's my pleasure to introduce our speaker today, Dr. Joon Kim. He joins us. He is a research scientist at Boston University, working with Toshi Nishimura, studying cold plasma dynamics, wave plasma interactions in Earth's magnetosphere, and neutral winds in the F region.
Yeah.
Um, and before joining BU, Joon was a graduate researcher at Southwest Research Institute, got his PhD at University of Texas San Antonio. And yeah, so thanks for joining us, sharing your research.
Thanks. Hello, everyone. Thanks for being here today, and thanks to Kevin and Eva for organizing this seminar today. And yes, my official name is Myeong Kim, but usually go by Joon, so you can call me Joon as if you want. And I'm really excited to share our research, and today, and I'm going to talk about the low energy plasma contribution to the visceral mode closed wave and pulsating wave. So let me start with a brief history of the visceral mode waves. So in the 19th century, the telegraph operator heard something like strange sounds, such as like the high pitch whistling or rumbling when they sent a message. And here are several reports about the mysterious sounds when they heard. And then also the interesting point is there are lots of the reports from the soldiers during the World War era. And so at the time, they thought that the kinds of the ghost or haunted sounds, but that is not the ghost or haunted sound, because the scientists in the early 20th century, they tried to look into this mystery sound, and they found that sound is related to the wave propagation in the outer space. And then 1953, that is the first concept of the modern concept of the visceral wave after confirmation of the ionosphere. The story they proposed that concept by using the wave propagation between the ionosphere and magnetosphere. And that concept was supported by the lots of the ground-based observation, because it's black and white scale, but they definitely captured the wave signal. At the time it's called like a VLF wave, but they capture that signature from using the ground-based observation. And then the early scientists, they're really genius, because they understand, they realized using this wave they can trace the plasma magnetosphere structure, because they realized that waves can be trapped in the plasma density dot in the magnetosphere. So at the time, they named it as the nose visceral or capital needs. And 1 year later, they made a first map of the plasma magnetosphere structure, depending on the plasma density. And they found some plasma pulse. I think can be back to the nose visceral or capital needs. And also they found at the time like the magnetosphere and plasma sphere perfectly using the ground-based observation. And also, they realized the high energy particle precipitations are related to the visceral waves, because like the 1963, I think that is the first space public weather about the high energy region, because they reported the energetic particle precipitation by visceral wave to the New York Times article. So I think that is the first public reach from our community to explain what happened in the high energy region. But based on that, these are kinds of the ground-based observation. But right now we are living in the spacecraft mission era. So that means there are huge amounts of data from the in-situ measurement. So here, this is one of the figure from the NASA headquarters, I guess, the Heliophysics Digital Resource Library. And as you can see, we can have like a 563 terabyte in the compressed data set, and you can see like the 600 terabytes per volume. So because since we are living the huge amounts of data in from the spacecraft mission, there are so many bunch of papers related to the physical mode waves. So if you search the science paper on the Google Scholar, then you can find some over the 30,000 paper within 0.1 seconds. So it's huge. So what characteristics do we know about the physical mode waves? Yeah, because there are so many papers. So it is really impossible to discuss all of the features in that wave. So I'm gonna I'm gonna do overview briefly. So one of the biggest contribution from the spacecraft mission is we found that the magnetosphere is like the jewel of plasma waves. So in this figure, you can see this is only one single trajectory spacecraft. But we can see lots of the part of the plasma wave in the different frequencies. Like you can see the physical mode wave here, and plasma spheric phase wave, another type of physical mode wave, and also you can see the electrocyclotron harmonics wave here. And then using that data, bunch of data, we found some favorable location of the different types of the waves, right? For example, physical mode cross waves are discrete from the night side to the lake side through the dawn sector, and whereas the another type of the physical mode waves, the heat waves, they are confined inside the high density, high plasma density region, and also we can see some magnetosonic cathedral noise or fat magnetosonic waves near the cathedral plane, and here is the electromagnetic ion cyclotron waves because due to the trajectory of the ions. So there are a bunch of the crazy party there, but in this talk I'm going to focus on the physical mode crosswave more. And so typically the physical mode waves are electromagnetic emission with a parallel propagation with respect to background magnetic field. And their frequencies are located into the two bands divided by half of electron gyro frequency. So they are called as like the upper band and lower band depending on the frequency. And using the spacecraft mission, we found their dependence on the of the geomagnetic activities. So this is the dependence on the AD index, so quiet time, the middle of time, and very strong time like the more than 300 Tesla. And you can see some gradual increase of the low crosswave amplitude depending on the geomagnetic activities. And also we can see we also see some propagation properties depending on the with respect to emission type, because here is the wave normal angle versus the wave normalized wave frequency, and you can see from the parallel to oblique, the electromagnetic emission converted to the electrostatic, because this is the magnetic field amplitude, and this is the electric field amplitude. So we can see the transition from the electromagnetic emission to the quasi-electrostatic when they propagate to along the field line. And also another key feature of the crystal mode crosswave is they do not show like the continuous elements. They are consist of something like the discrete elements, and what we can see here is we can see there is some variation of the amplitude even though within a few seconds. That means that phenomena is called like the wave modulation, and that modulation time scale change from a few seconds like that one, or can be a minute scale. So that is one of the key feature of the cross wave. But we can ask the fundamental question: why do we examine that wave? Just a wave. So why do we need to examine that one? Because these waves is the most important part in magnetosphere dynamics, because they are one of the primary driver to accelerate for the electron acceleration to build a radiation belt around the Earth. And also, as I mentioned earlier, these waves are also can scatter the high energy electron into the atmosphere, which is called energetic electron particle precipitation. So for the space, for magnetosphere dynamics and the space weather purpose, they are really important the phenomena we have to examine. So then another question, fundamental question is, so there is a wave and they affect us on our system. So then how can that waves generate? So it is widely accepted that using the linear theory, that waves can be extracted the free energy from the injected electron from the plasma sheet, and that electrons have an energy range over the greater than a few kilo electron volts, and then typically they have a significant temperature entropy in the perpendicular direction. So that means they are very unstable to drive the visceral instability. So after that, they can excite, that condition can be a favorable condition to excite the cross wave. But here, the interesting point is, after excitation, they do not give the continuous growth rate. Instead of that, the system adjusts dramatically, which means they are restored. That system should be restored to the stability after the cyclotron resonance. So and using the linear theory, that the upper threshold can be derived, and that the threshold can be represented by the function of the temperature and entropy and the parallel beta. But here, the temperature and the beta is based on the hot electrons. So that the threshold have been confirmed by the in-situ measurement in the microsphere at the quantification. At the first four figures show the cross wave observation depending on the temperature, entropy, and parallel beta at geosynchronous orbit. And this straight line is the threshold I mentioned. I showed you before. That line, and they shows like they are combined by the straight line below that straight line, and it is called like the marginally stable state. And it can that stable state in the microsphere using the bar and cross, like the inner microsphere, and also using the cluster data. The cross wave are also combined by the marginally stable state at the bottom of the sheets. But however, what I talk about, like by now, I talk about the most of the contents are related to the hot electron or hot plasma. But my title is like the low energy plasma. So we're right there. So right now I'm moved to how to connect the low energy plasma and the cross wave. Yeah. So due to the space potential, it's really hard to measure the low energy plasma, but there are actually the genius people, scientists previously, so they analyze their origin and their the drift path in the microsphere. So as you can see, there are several different origin of the low energy plasma, such as the plasma sphere, and also there are some one plasma flow, and including not showing here, but they can be included. The ionospheric output can be included that population, and also there are some people talking about the low energy plasma directly from solar wind. But anyway, there are a bunch of the different sources of the low energy plasma, and when we remember the low energy, the cross wave, the favorable location of the cross wave, definitely there is a overlap region. So what feedbacks are there between two different distinct population like that? Are they independent to each other or any contribute to each other? So to make it short, yes, the answer is the cross wave strongly affects the low energy plasma strongly affect the cross wave or properties. For example, here the color shows the different wave frequency normalized by the tidal electron cyclotron frequency, and this is the wave vector versus the low energy plasma density. And as you can see, wave vector are affected by the increase with the low energy plasma density here. And so that means their resonant conditions are affected by the low energy plasma density. As a result, there is a growth rate also affected by the low energy plasma density ratio over density. And also the point is, the interesting point is at a certain point when you see some maximum growth rate here at some point the growth rate increase with the low energy plasma density, but at certain point they decrease with as the low energy plasma density increase. Also, by changing the growth rate or wave vector, the saturation amplitude also affected by the plasma density ratio. So here, when we compare to high concentration of the low energy plasma versus such a zero contribution of the low energy plasma, you can see the wave saturation amplitude and growth rates are affected by dramatic change here. And also, lastly, the incidence threshold can be reduced by the low energy plasma density ratio. So theoretically, the high energy gives the pre-energy. The cross wave can be extract the pre-energy from the hot plasma, but the cold plasma or low energy plasma, the effect or the most of the wave properties such as the growth rate, the saturation amplitude. So, but I said that is kind of the theoretical approach, but the previous observation study, they didn't consider any presence of the low energy plasma. So that's the reason why we see some marginally stable state of the cross wave after excitation. So, for example, at this figure, this is from the UL 2016 using the Barring cross data, and they show the cross waves during the cross waves, they are combined by the stable state. But considering the continuous signal of the cross wave, it can be a little bit difficult to understand why the cross wave signal be continuous at the time. So because at the time, this paper or the other previous paper, since they do not consider the low energy plasma, so we don't know how many waves are literally in the unstable region if we consider the low energy plasma. And also, there are three ways for the wave modulation, and to explain the wave modulation here, like the variation of the temperature ratio or variation of the pattern, and also can reduce the threshold by changing from the time the low energy plasma modulation. So here there are 2 points here, like how many waves observation literally in the unstable region if we consider the low energy plasma, and also what is the most important factor for the wave modulation based on the linear theory. So to understand that questions, we survey the low and cross wave from using the previous mission AD and E from 2012 and 23 or almost 11 years. And then here is the identification of the cross wave for the statistical analysis. So we only focus on the low band cross wave with their amplitude is greater than 20 picotesla, and also we excluded any heat wave by applying some by removing some the high density region. And then lastly, since the TMIS does not have any wave mnemonic information routinely, so we calculate the EB ratio to focus on the electromagnetic emission only. And then here is the figure show how we identify the cross wave here. There are two strong cross wave signal, first and later, but the first one was observed in the high density region, so we excluded that one. So we only picked the second one, except for the periods less than 20 picotesla. So after solving the cross wave, we examine the relationship between the wave amplitude and the linear instability, depending on the low energy plasma. And here, in this study, the definition of the low energy is their energy is less than 800 eV because most of the time the cross waves are interacting with the kilo electron volt, more than kilo electron volt. So we think 800 eV is enough to take the background non-resident population as a background the population for the cross wave. So here is the example of the we identify example of cross wave we identified, and then that event showed the importance of the low energy plasma on cross wave study. So from the top to bottom, there is a wave spectrogram and amplitude. Here is the low energy plasma density ratio, parallel beta, and temperature ratio. And the last one is the instability index from the threshold. So which means if that index is greater than 0, that means they are literally in the unstable region. So here there is the wave the wave variation shows the correlation between among the parameters here. So we calculate the correlation coefficient for each parameter, and then we found points that the highest correlation was observed in the low energy plasma density ratio. That means in this case event, the wave modulation is totally efficiently controlled by the low energy plasma variation. And also when you see when we check the stable or unstable condition during this time, definitely if we calculate without low energy plasma, definitely they are confined by the marginally stable state, like less than 0. However, if we add that the contribution of the low energy plasma, that index shift to the above the 0, which meaning that they are literally in the unstable region. So that here the wave modulation and the real the wave the instability condition is favorable for the excitation of the cross wave by adding the cold plasma. So I said we have a bunch of the data observation. So we move to the statistical result here. So here is the temperature ratio versus parallel beta, depending on and showing some cross rates for each cross wave individual observation without low energy plasma at the time. So this is the stabilism occurrence rate, and this is unstable. So as you can see, there is only 4% occurrence rate in the unstable region. That means they're very consistent with the previous study because they are definitely confined by the marginal stable state. However, if we consider for each individual low energy plasma, the occurrence rate in the unstable region increase up to 31%. That means the total wave observation from the total observation, just only we can simply add by adding the low energy plasma density, we can explain 31% can be excited because they are in the unstable region. But however, we can still have around 70% or 69% are unstable region. So that can be explained by some modulation, wave modulation later. So before that, we also check some dependence of the low energy plasma for EV ratio and how they are distributed in the temperature ratio and parallel beta. So here, interestingly, you can see some critical transition between the lower population to the higher population based on the low energy plasma density ratio around 0.1 parallel beta. And also, you can see the electromagnetic emission from wave can be converted or changed from the electromagnetic emission to the mixed type of the emission around parallel beta 0.1. So in detail, we need separate some higher and lower concentration around, depending on the point density ratio is around 0.8. You can clearly see only 8% of the waves are electromagnetic emission in the higher concentration, whereas the strong electromagnetic emission can be seen, or around 50% can be seen in the lower concentration. So is this new one? No. That transition also observed by the previous study and the numerical simulation. So here, again, from the 2016 paper, they uh, they checked the parallel beta versus wave normal angle, and they found some critical transition to uh, from the parallel to the oblique propagate around 0.025 on that parallel beta. And also simulation also shows some the parallel oblique to the parallel and electrostatic to electromagnetic emission at the 0.025. So this transition is due to the cyclotron resonance condition because in small beta region, that means the small beta means their electron temperature is low. So that means based on the electron condition, the small temperature means their wave should be large enough to resonate with to resonate with the electron, but that wave vector cannot be infinite. So that's the reason why they move to oblique and the electrostatic emission from the electrostatic instead of the electromagnetic emission. But here the difference point is our data shows the around critical transition occurs at around 0.1. I think since we don't have any wave modeling information, so we don't know about what the exact critical transition from our data set. So that I think that might be some effective for our results. So that's the reason why we have some higher critical position points compared to the previous one. So I said the 69% still inside the unstable, still inside the stable region. Then how can be excited even though they are stable region? So we think we think the modulation key factor to give positive growth rate to at the time because even if they are confined by the marginal stable state, then small variation of the linear exciting parameter can give free energy and the growth rate enough to excite the growth wave. So based on the linear theory, the growth rate can be represented by the function of the combination of the fractional density of the electrons and temperature and entropy. And here, that is the temperature ratio, but the resonant electron density, they can be modulated by the parallel beta and also low energy plasma ratio, since they reduce the threshold. And also they can go back to the total electron density. So the modulation study also have been widely investigated using the several mission, like the CMS and Bahrain probes, and also the bottom figures are also from the CMS mission. And then they found which parameter is more important, like and then mostly they found some positive correlation between the wave amplitude and the density enhancements. And here is the also density enhancement, and DD is at the density depletion. But the point is, they only check the total electron density. They didn't examine how the low energy plasma contributed the total electron density. So still the contribution of the low energy plasma still remain unknown. But
Sorry, when you say density enhancement and depletion, is that some like local, like?
yes, yeah,
local
this
structure?
like local when you just when you see some the temporal profile of the density, then you can see some like the structure.
So it's literally just an enhancement.
Yeah,
or-
enhancement without that depletion. So in our study, let's say the 69% are in the sleep region. So we modulate and say modulation is a part of mechanism to make the wave excited. So we calculate the correlation function for each cross wave events. And then here is the distribution of the relation coefficient between wave amplitude and temperature ratio, parallel beta, then low energy plasma. And when we check the positive events only, then you can see the 66% is mostly correlated with the wave amplitude, which means low energy plasma is also a factor for the wave modulation. Is that? But we can see the temperature ratio and their contribution to wave modulation by the temperature ratio and rate of wave. But yeah, they can be contributed together, but the most dominant factor is the low energy plasma here. That is the total events, but if we focus on the state case here for events, not the single wave observation, then we can see some positive correlation coefficient between where the wave amplitude is around 66%, and among them, still the low energy plasma is the most correlated parameter for for inside in the scale category. But there are still some but in that category, 34% show some negative or weakly correlate with the linear instability. There are so multiple factors to explain that one, but here is the two one. Here are two, like because the number of the resonant electron decrease as the minimum resonance increases. That means the low energy plasma doesn't or the lower the few density can be participated at with the cyclone resonance. And also, I briefly mentioned for the theoretical part, the high density from the low energy, the accumulation of the low energy plasma would start the wave growth, because we can see the wave growth rates decrease at certain points, and in theoretically, the low energy plasma increase the direct constant of the plasma, and that affects the electric field participating in the instability. But we have to check that contribution in detail more. How many minutes? 18. Okay. So we checked for the wave itself. We found the most important part is the low energy plasma. So let's move to the interesting phenomena related to the cross waves. So which is called pulsating aurora. So pulsating aurora is kind of one type of the diffuse aurora, and this is very special because the aurora brightness looks like the on and off brightness with a few seconds to tens of minute scale. That means, and I think when I talk, and I already talked in the early slide, I said the modulation time scale is like a few seconds to the time minute scale. That means, yeah, definitely they are correlated with each other. So many of the observation previous work found that the cross wave intensity perfectly correlate with the aurora brightness during the pulsating aurora. So they thought that due to the wave modulation, they scatter more electrons into the ionosphere and that caused the pulsating aurora. So right now we know that the cross waves are main driver of the pulsating aurora. But the point is, there are still controversial that what instability factor could drive the pulsating aurora and wave modulation at the same time. The study, the result I showed you before previous slide, that is only wave itself. But if we add some if we survey the conjunction events between the pulsating aurora and wave modulation, that result should be constant, like the low energy plasma still important, or another parameter can become more important. So that is the our another science question. And the last question is, so what population can explain the patches motion? Because the for a long time, the aura patches are following to the cold plasma, low energy plasma in the myosphere, because they are following to the equal speed drift pattern in the myosphere. So they are still, but during the Pulsating Aurora, when hot electron generate the cross wave, and they don't have any contribution to the patches motion. So that is the other last question in this talk. So to investigate the modulation of the Pulsating Aurora and wave intensity at the same time, we again surveyed the conjunction events between the Pulsating Aurora and the low band cross wave using the DMS mission on the night side. And the survey period is around from similar but more longer than the previous one. And then we found 19 conjunction events. And this example shows how we identify the conjunction events here. So first of all, okay. So here there is a south onset, and that should be transit into the Pulsating Aurora. And here the partial constraint is that phenomena, that transition should be located near the or at the genesis of the Earth sky emission, because we have to trace or we have to check the aurora patches motion. But it happens the far away from the genesis, then the fundamentally the Earth sky emission is that motion can be destroyed by as the distance increase from the genesis. So we understand the exact or the low uncertainty of in the motion. We have to check. We only pick the potential events when that transition occurs at the genesis or near the genesis only. And then at the time, the theme is here the theme is A, and theme is A footprint should cross the Pulsating Aurora region near the genesis again, and then at the same time the theme is wave the instrument should observe the wave generation for lower band cross wave. And so using that, after the finding some conjunction events, again we also examine the relationship between wave amplitude and other three parameters like low energy plasma, density ratio, and parallel and inverse ratio. So which one is become more important than during that transition time? So here is the example of the wave modulation associated with the low energy plasma density ratio. Yes, here we okay. So here is the streamer. Okay, got it. The streamer, and it turned into the Pulsating Aurora at the near the genesis, and also we can observe both of the themis D and E observe the cross wave at the same time in the time, but the themis D is relatively close to the genesis, so we only investigate the themis D data here, and this is the wave amplitude versus the plasma parameter from the low energy plasma temperature ratio and parallel beta. Yes, and then when we see that the most correlating parameter is can be seen in the low energy plasma density ratio highlighted by the blue arrows. And also, yes, there is some short period. There is a period the other parameters correlate to each other, like the for temperature ratio. We can see some here, a little bit here, or for beta, which you can see here. But compared to the low energy plasma, that period is much shorter than the general the low energy plasma. So we think in this case, even though multiple the parameter contribute to the wave modulation, but the most dominant one is the low energy plasma density ratio. So and then so as shown in the video, during the Pulsating Aurora, we can see some dominant wave towards patches motion, but that is the optical data, which means in that patches are inside the Earth's rotational frame. So we have to calculate them to compare the cross speed, and then here this is the east-west cuboid from the video, like just like the center slice of the theme is from the west to east, and then trace the pulsating aurora structure inside in the non-rotational plane after correcting some Mars rotation. And then here the negative means that patches move to westward in the non-rotation plane, and here positive means the move west eastward. And then, as I mentioned, the aurora patches gives due to the convection pattern in the multisphere. And here we calculate the two types of the equal speed drift. First one is just like simple assumption that ion work velocity follow to the equal speed drift mostly. And then second one, we can directly calculate the equal speed drift from the electric field measurement. So here is the two types of the equal speed drift. And of course, the second panel show from the field measurement, and the first one is the ion work velocity from the ESA moment. Well, anyway, there was a little bit difference between two different approaches, but the equal speed trend is mostly similar to each other. So we think EPI is okay to use them all, then compare and that speed compared to the patches motion through the optical data. And yes, following the previous study, the most of the patches speed or the directions are compared to the equal speed drift. So in case events, the modulation and patches motion are controlled by the low energy plasma, definitely. And however, the other conjunction events show totally different, which means again there is a injection happens, and can see some injected particle from the pulsar forward, and then there is that even though there is some light contamination, but we can see some pulsating aurora patches here. And in this time, the most correlated parameter with the wave amplitude can be seen in the hot temperature ratio, highlighted by the blue arrows, and then here's that line is above the 1, which means the anisotropy, the perpendicular anisotropy index. And then you can see that the wave amplitude increase when the temperature ratio is greater than 1. That means definitely these events are controlled by the temperature ratio. And also, but the point is here based on the optical data, there are some eastward motion, but mostly during the pulsating aurora period, they move to westward based on the optical data, which means they are still following to the cold plasma structure. But as I said, they are inside in the rotational frame, so we have to check the non-rotational frame again. So we think so temperature ratio modulated waves modulation. So we think that patches motion would be reflected by the hot electron temperature motion too. But when you check the similar way, like checking the trace motion in the non-rotational plane, the speed is still like the 56 meter per second to eastward, like the 600 meter per second to eastward, 100 meter per second. But when you calculate the bound average velocity in a type of field assumption, the minimum should be like over the 20 kilometers per second, which means the highest eastward patches is even, yes, assuming just using that one, like 600 meters per second. It's still like the 30 times slower than the fast average multi-drift motion. So, but still, equal speed drift shows a comparable speed compared at this time. So, but wave modulation or pulsating aurora patches modulated by the temperature ratio, but the motion is controlled by the equal speed drift by the cold plasma. So is this example an exceptional or something weird? But based on the 19 events, we found that the most of the events are correct, shows the high correlation with temperature ratio, but and then the low energy plasma is the second contribution at the 42% and 26%, and the other like a mixed parameter or parallel beta is around 16%. So, but when we see the patches motion, definitely there are most of the data, most of the events show the westward dominant. But we can see that means the patches are mostly controlled by the cold plasma structure in the myosphere. But we can see some eastward motion here, so we have to check the which that motion, whether that eastward motion whether follow the whether cold plasma structure or not. So again, we track all of the patches in that data, not just like a representative and evident patches motion, and calculate the equal speed using the electric field measurement, and then assuming 1 keV and the minimum resonant energy, we calculate the mark eastward drift speed. And here, as you can see, most of the patches are followed to the one-to-one relationship between the equal speed and patches speed. And yes, they are not perfectly one-to-one, and there are some deviation or outlier over there, but still most of the patches are following the equal speed drift in the myosphere. And that outlier can be explained by some might be some uncertainty using the mapping problem, because in this study we focused on the transition from the substrate onset to the pulsating aurora. That means the field line is not that simple. There should be more even though we calculate the dipole field line mapping or the listen model from the SIG, there is always 10% on mapping uncertainty between depending on the model. So I think then they might be affected by the mapping uncertainties or electric field offset problem, even though we calibrate the electric field to calculate the equal speed drift speed. But here for magnetic drift, just ignore just only for the eastward motion. Yeah, still their patches will still less than 2 kilometer based on the optical data, but the for visual resonant energy and 1 kV, that's the corresponding magnetic speed is much better than the patches motion. So we cannot explain that motion based on the hot electron motion. So how does temperature ratio modulate the cross wave while the cross wave and pulsating aurora together at the same time, but while the patches follow the cold plasma structure in the myosphere? So here is the possible scenario. So first, when the hot electron moves along the magnetic drift line with a time varying modulation of the temperature ratio, they can overlap with the cold plasma structure traveling along the convection pattern. And at this time, the cross wave can be modulated due to the time varying temperature ratio, and then at the time that wave can scatter electrons into the high electric region, and it causes the pulsating aurora. And so as a result, that pulsating aurora patches, brightness, and wave modulation, they are synchronized with the time varying temperature ratio. However, the cold plasma of the patches are attached to the cold plasma and to population drift independently. So the patches can be explained by the cold plasma structure only, while the drive mechanism is based on the hot plasma. So previous study also suggests the concept, but there are some difference between our data set, because the 1983 study level, they proposed the similar concept, like overlap with the cold plasma, but they assume there is some stream, continuous stream electron, hot anisotropy electrons. But our data clearly showed that the temperature ratio shows some time varying along the trajectories. And also another scenario proposed by the Nishimura 2015 inside they make emphasize more to importance of the low energy plasma more, but in that study there is no any clear conjunction events between the Pulsating Aurora. Like they just only calculate the positive relationship between the low energy plasma and the wave intensity only, and then that is just like a proposed scenario of the Pulsating Aurora patches, but they didn't examine any conjunction events between the two phenomena. So, but you miss something here because in our study we use only linear theory, like based on the linear theory parameter, like the temperature ratio, the parallel and low energy plasma. We don't know about that means we only focus on the linear scale of the cross wave excitation, but absolutely there is a non-linear stage to excite for the cross wave. So, and then that topic cannot be conducted by current surveying mode of the image. So we totally miss the contribution of the non-linear contribution. And also, as I said, the TMIS observation does not have any wave node angle information. Instead of that, we use the strong wave amplitude, less and lower EV ratio, but they can be still there can be some overlap propagation, not the parallel propagation totally. So we don't know about them. Also that the propagation effect can be contaminated or affected our research in this study. And this is last slide. So we have to discuss about the possible source of the time varying temperature ratio. But we didn't check any. We didn't know the exact source of the time varying modulation, but we can think about some possible sources like the multiple injection but we cannot see any other. But multiple injection happens, but you cannot see that signature from the first sky imager. And also, this is just one single trajectory, so then we do not know they can be from the continuous multiple injection from the plasma sheet or local phenomena, whether they are local phenomena. And maybe I think I searched some paper about that one, and January 2025 is talking about some electron fiber force integrity can increase some time varying temperature, but I didn't check that contribution in detail. Also, there is the TMIS does not affect that much, but the Los Alamos geosynchronous or the that spacecraft, they sometimes charge negatively more than 1 kilovolt, and they found that space potential affected the electron temperature and fluxes. But the TMIS does not go that high spec potentials, but But still, there is a possibility room to affected by the spectral potential. And also, this is the biggest topic, one of the biggest topic in our community, which is the where that low energy plasma structure come from. We don't know about it. They can be ionospheric outflow or turbulence, or generated by turbulence, and also very interesting paper like the equal speed gradient instability, including some polarized electric field inside the inhomogeneous plasma condition. So they can generate some fine scale, like the highly structured of the low energy plasma, and that can be our future. But yeah, if you are interested in that topic, just please let me know. We can definitely collaborate together on how they can be generated and how they contribute to the visceral mode waves later. So yeah, this is my last slide. Thank you for listening.
The question. So you're saying low density structures, like there's some enhancement or depletion in the density of the cold population of the plasma. But the parameters, as far as I could tell that you were using, in your correlation analysis was the density ratio.
Yes.
So, is it always the variations in the cold plasma density, or can you also have?
Oh, yeah, there is also, there are also hot electrons hot electron density more important than some cases. So nothing here, but some events show that there is a density enhancement, but lower plasma density ratio decrease during that dose. So that means they can be from the more particle concentration than enhancement. Yeah. Mostly we can see most of the data show the lower plasma enhancement correspond to the total electron density enhancement. Yeah, but I cannot say how many portion. Yeah, I didn't check it out.
Just want to make sure I understand. Is there any way to make sure that the measured wave intensity is at the same location as where the waves were generated?
Yeah, that's really.
They have not
Yeah, that's right. Yeah, then here most of all of the events we compile the magnetic equator like the plus minus 10 degrees latitude. But yes, the source region can be different at some points. So, but we don't know what wave normal information. So but based on the statistical research previously, the equator plane might be the best source region we can guess. But yeah, that's the good points. We don't know. We cannot make sure 100% sure they are directly from the source region. Yeah.
So whether or not this region is unstable.
Yes. Yeah, that's right.
It's kind of a
Yeah. That's
yes on
yeah.
indirect.
Yeah, that's right. But at least including that uncertainty, we see is that we saw the occurrence rate dramatically changed from the 4% to 30%. Yeah. I think we think that the low energy plasma by just simply on the linear stage, simply just adding the plasma low energy plasma, we can explain the excitation of the cross wave simply. But I said we don't know what the non-linear effect right now. So
Why can't you get the wave normal angle from Themis? Are they doing like some onboard?
yeah, that's the onward problem. Because the Barrington they gave us like a full compound of the FFT
Yeah.
free expense from the data, but that is the automatically transformed from the space onboard. So we don't have any information from them. Also. But I think Himis also has some burst mode and what kind of like MMS. And that mode we can using that mode we can calculate the wave normal angle and other wave properties such as the eclipse polarization, but we are using this just like simply similar to MMS survey mode, so we don't have any information there.
Any other questions? Not, let's thank our speaker again.